Hello, welcome to our webinar. Today we're going to learn how you can become a creator from being a player of video games by using TileCode, a platform that was developed at Microsoft Research by Thomas Ball. And I had the pleasure to do a user study over the summer using this platform, which we will talk a little bit more about in this webinar. Why does it matter for people to become not only players of video games, but also creators? Today, we know that the number of gamers has increased worldwide, and we have almost around 2.6 billion people who are active players of video games. We also know that games and video games can be used as a source of enriching creativity and storytelling, and also as a source of critical inquiry. These are a couple of books that we came across in our research that we think are underlying these ideas. When we talk about video games and children, we know that children have a wide experience with games and a rich intuition about how video games work. We also have seen that games can be a powerful tool for introducing a computational vocabulary. Today, we actually have the widest online platforms for coding for children be designed around video games with examples as Minecraft and MakeCode, Scratch, which are platforms with millions of users and projects that are being shared. However, none of these platforms work on handheld devices, and this is where TileCode comes into play. TileCode, the best part about it is that it works on handheld devices and handheld arcades such as the Meowbit. These handheld arcades are not new. They've been around for a while, and there's a wide community of users that exist around these devices. However, most of the games currently accessible on handheld arcades cannot be programmed on the same devices, which is something that TileCode is trying to address.
All right, thank you, Steph. So the TileCode challenge is how to program games on these small devices. Our solution is to constrain the programming paradigm so that you can program using the A and B buttons in the D-pad, yet enable the creation of a variety of games. And in order to do that, we take our lead from board games, where we have pieces that move on a chess or checkerboard. So what's critical to those games is that you have a two-dimensional grid. The grid has squares, and you have pieces, and you go from a current state to the next state by moving a piece, like here in checkers. In TileCode, what we're going to do is we're going to have a grid as well. It's called a tile map. It's the foundation of retro video games. And we're going to have backgrounds of the tiles, as well as sprites that occupy tiles. And then we're going to be able to program with TileCode so that the sprites move in a particular way. And so just like with board games, we have pieces, which we call sprites, and they move to adjacent tiles. So in the case of TileCode, sprites can move up, down, left, or right. Now, we want to make video games, not board games, so we have other things we want to keep in mind when we're developing this programming model. We want to be able to respond in real time to user events, like button presses. We have non-player characters that move on of their own accord, and we want to be able to program those. And furthermore, all these activities are happening concurrently, in parallel, so we need a way to express these concurrent or parallel activities. We use 2D cellular automata as the foundation of TileCode. In 2D cellular automata, you have a grid, or a matrix of cells, and each cell has a value from a finite set. Here we have three possible values: blue, orange, or white. Then we give local update rules to take us from the current state of the automata to the next state. In this case, we're saying that the middle square here, which is outlined in red, becomes orange in the next state if the cell above it is dark blue. And the stars mean we don't care what the values of the other squares are. So this is a local update rule, and these rules are applied in parallel. So this gives us a lot of power. Here's a current state in the cellular automata where we have 6 dark blue squares, and the next state given by the local update rule would change every cell that's under a dark blue cell to orange. So cellular automata are great, but they're not the best for programming games. So in TileCode, we separate backgrounds and sprites. The backgrounds are like the values we would put in the cell of an automata. We have 4 possible backgrounds for every tile. But then we have movable objects. These movable objects are called sprites. And here we have 4 different sprites. So every tile has a background, but a tile can also contain one or more sprites. Sprites, furthermore, as you recall, can move in one of four directions, or they can remain at rest. And so we also have a way to refer to the state that the sprite just moved in, either left, up, right, down, or the circle means it's at rest. So here's an example of a sprite controlled by the player that's moving around the tile map, and you can see the direction that it's moving by the arrow. Okay, so now to TileCode. The user interface is created to be able to run on a gaming handheld. You see the D-pad on the left and the A and B buttons on the right. And TileCode uses the tile-based interface as the way to create games, as the way to design and create games. TileCode starts with the load screen, in which you have 8 different slots for the 8 different games that you can create. From there, you can select a particular game and go to the game home screen, where you have access to the 4 sprites and 4 backgrounds. You can choose among different sprites. You can also place the sprites on the tile map. So to create the initial level of the game, you go to the map editor and place the sprites and change the backgrounds of the tiles. And finally, you can also go to any sprite or background, and you can use the paint editor to change the artwork for that background or sprite. The foundation of programming in TileCode is the when-do rule. This is a form of guarded command. On the left-hand side, we have a pattern. Here we have a pattern that says there should be an elf at the center and some green grass or blue grass to the right. So this is like what you saw in the cellular automata. We also have an event, which is the right button press. So the way to read off the when side of this rule is that when the right button is pressed and there is this blue grass to the right of the elf, then we're going to fire the rule and execute the commands on the right-hand side of the rule, which is the do section. And in the do section, we see we're sending a move right command to the elf sprite. So we have a very simple visual programming paradigm that allows us to pattern match on the tile map, as well as refer to events, and then send commands to the sprites. That's the essential of TileCode. So a TileCode program then is simply a set of when-do rules. Here we see 3 rules. The rule I described already for moving the sprite around. The elf sprite, if it collides with an apple, then the apple is destroyed and 10 points are added to the score. This is a second rule for eating apples. And the third rule says that if the elf sprite collides into a snake, then it's game over. So a TileCode program is a set of these rules that are essentially run in parallel, as in the cellular automata. The when side of the rule, you have different events. We'll see those. There's pattern matching against the 3x3 grid around the sprite. And there's a way to bind a sprite so that you can send commands to it. So there's a number of very basic programming language concepts that are embedded in the language. The do commands are quite simple. There's a set of move commands to send to the sprite. You can destroy a sprite. You can paint the background of a tile, so you can change the background. You can create a new sprite. There's a set of game level commands for game over and adding score. And there's a special command called portal, which we'll describe later. We've created a number of games with TileCode, and here we show the dynamics of 6 games. And under each game is the number of when-do rules that were required to create that game. So in the upper left, we have the snake game. We have a game for pushing boxes around, turning them into diamonds. We have a game on the upper right for eliminating 3 in a row or a column. We have a mining game in the lower left. We have a jumping game, avoid the snakes. And then we have a sort of dungeon game. And so you can see here 2 to 3 handfuls of rules, 9 to 14 rules were all that was needed to create these particular games. And they're quite playable. So now we're going to transition to a demo, and we're going to show you how to create the snake game completely in TileCode using just 9 rules. To just give you an idea of the game informally, the user has control of a snake that's moving continuously through the tile map. Here the game ends if the snake head collides with a barrier or the snake body, as shown by my very fine art. So here's the snake colliding into a wall. That's going to be game over. The snake should act like a snake. Well, what does that mean? It means every segment of the snake follows the segment in front of it. So somehow we need to code the snake to move like a snake. And finally, when the snake eats an apple, it's a funny sort of snake, it grows by one segment every time it eats an apple. Okay, so now given all that setup, the informal description of the game, let's transition into TileCode to see how it actually works in practice. Okay, here we are in the TileCode application in the web browser, and we have 4 sprites at our disposal. We have what I call the snake parent, the snake child, the apple, and the apple core, and we have some backgrounds. So these have been already set up. We have a tile map which we've already created, where we've placed the snake and some apples. It's a rather large level. There's some apples inside ponds. And so this is a static image, and it represents the initial state of our game. So what we'd like to do now is step-by-step add behavior to the game. This is the programming aspect. The first thing we like to do is give the user control of the snake parent. So in this page, we have a set of different types of rules we can choose from. We want to choose the press event because we want to have the snake parent move based on what the user does. So we select the right arrow of the D-pad, and we get a rule. And what we want to do simply here is have the snake move right whenever the right button is pressed. Now, TileCode does something for the first sprite, which is usually the player sprite, and it generalizes the rule for us to the other 3 directions. So here's the rule for the button up press event, where we move up, we move left for a left button press, and down for a down button press. With a single rule that we've given, by example, we now can make the snake move 1 step at a time. So notice every time I click on the D-pad, the snake moves. Okay? And if I hold the button down, it keeps moving. But recall, we want the snake to move continuously. So once I press the button, it should keep moving in that direction. So for that, we have to go back to the rule selector menu, and we have to think about what happens when the snake has changed state. And in particular, we have this rule that says the snake has just moved right 1 square. So this is the state of the snake. It has just moved into the middle square, and it has just moved right. So in this case, in the absence of user events, and there are none in this case, we are going to keep the snake moving right. So with that simple rule, a snake that has started in motion continues in motion. So now you can see we take 1 button press in any direction, we change the direction of the snake, and it keeps moving in that direction. We want the snake also to start moving from the resting state. And so here I'll show off the feature where we can change in a new rule the direction, or the predicate over the direction, to the circle. So circle denotes the snake at rest, and in the initial state, all sprites are at rest. So in this case, we want to start the snake moving right. And we actually want to stop generalizing. If we were to keep generalization in this case, the snake would randomly choose one of the 4 directions to move, but we really want it to start moving right. So now with no user event, the snake starts moving to the right. Okay, but as you notice, it can move anywhere, and there's no particular actions that take place. So let's return to the rule selector screen and add a collision event. So we call this smash events. We're going to code a rule for when the snake parent crashes into various items. So we want the game to be over when the snake crashes into the wall. So we select that. Notice we can add the wall to the set by clicking there. We also, this snake doesn't like to swim or go into the grass. Strange snake, so we check that. And also if the snake wraps back around on itself and smashes into one of its children that's following it, then it's going to be game over. So we've chosen 3 things to detect collisions on, and we're going to just use the upside down trophy. So now we can see when we go into the wall, it's game over. When we go into the water, it's game over. And if we loop back around, it's game over. Okay, so let's actually not. The snakes like the grass, so they like to hide in the grass. So let's let the snake go into the grass, and we can see now that it does that. Okay, so now we've got collision rules. Now what we haven't done anything with the snake children. So the snake child, we can go and select it, and we see there are no rules present for the snake child. So the first thing we like to do is make sure that the children start moving in the same direction as the parent. And if you'll recall, that's to move right. So let's do that simple rule. The snake child at rest moves to the right. Okay, and what you see is that they're inching along. So why aren't they moving smoothly? The reason is when the snake moves to the right, it enters the moving state, and it remembers that for one round. But we don't have any rule for the snake child moving. We just have it at rest. So it takes one round for it to move, another round for it to transition back to the resting state, and then this rule fires again. So that's why the snake children inch along. Okay. As we saw in the PowerPoint, we want the snake children to follow those in front of them. So the way we're going to do that is with some new rules, and here's where we show off the power of pattern matching as well as parallelism. So when would we like to keep the snake child moving to the right? Well, if it should keep moving to the right, then there should be it should be following the element ahead of it. And where would that element be? Well, it would be to the tile to the right, and it would either be the parent or another child. So we want the snake. We certainly want it to keep moving to the right, at least in this case. But furthermore, we want to know that that segment itself just moved to the right. So this is a snake that's just moving along happily in one direction. Okay. So we're going to have the snake child keep moving to the right. If to the right there's another snake element that just moved to the right as well. And we want to actually generalize this to 4 directions. So that holds for going up or any direction. So this is the snake moving in a straight line. And as we see, if we let it go now, then the children are just moving along. But notice, as soon as the snake parent veers off, then the snake children return to inching along. So we definitely need some more cases. So another case is going to be that the snake child should move up next. So let's think about when it should move up. Well, if it needs to be following the segment ahead of it, then there should be a segment above it. And furthermore, that segment should just have moved up. So here we're turning a corner. So the segment ahead of us took a counterclockwise move. We moved this segment, moved to the right, so now it should follow its leader by moving up. And we should generalize that as well to 3 more directions. Okay, so now we can see that as long as we're moving counterclockwise, everybody's following along. But as soon as we move clockwise, we're back in the same old state with inching along. So we have one more case, and that's for the snake child to move down. And I think you can probably guess at this point where the leader should be and what direction that the leader should have been moving. And again, we're going to generalize that rule to 4 directions. So now we have a complete snake that moves wherever the parent goes. Wherever the parent goes, the children should follow. And you notice that this works for no matter how many children there are. So if we go to the tile map and we increase the length of the snake by, I don't know, 3 more children following along, then the pattern matching will just apply to all of those. So this is the power of the cellular automata approach, and the power we have in TileCode is that the rules apply over the entire tile map, and as a result you can achieve some really nice parallel effects and behavior with very little code. So I'm going to change the snake back. Actually, let's make it a snake of size 3 altogether. Okay, so what you've seen so far is we've seen the complete dynamic of essentially moving, having the user move the snake, and having the snake act like a snake as well as collide. So that's been a number of rules. Now we need to actually consider how to make the snake grow. And this is going to be another smash rule. In this case, the snake parent is smashing or colliding with the apple. And in this case, what we want to do is get rid of the apple. So this is the destroy command. and this destroy command applies to the sprite to its left. That's the apple. But we want to leave a leftover in its place, and you'll see the reason for doing that. We're going to leave an apple core. So in place of the apple, which was just destroyed, we're going to create a new sprite, which is this apple core. It'll be left at the same position, and it'll be created at the position. And we're going to increase the score by 10. So let's see what this simple rule does. This simple rule means that whenever we go over the apple, it immediately gets changed into the apple core. Whoops, I missed it. And we see that the score increases. So now how are we going to accomplish the final step, which is to grow the snake? So this is an interesting part. You notice that the apple, because of the movement of the snake, when it eats the apple, it will continue to move over the apple core until at some point the last child in the snake moves past it. So here's a snake child that's just moved to the right, and we want to consider the case when it is just past the apple core. Okay, that looks right, and it's the last one. And what that means is that in the tile that contains the apple core, there should be no snake child, and we do that with the red do not go here sign. So that means we don't want to see this sprite in the tile. Okay, so this picture is a little misleading. If we hover over, you can see it. So there should be a tile, the tile to the left of the snake child that just moved right should have an apple core in it, but should not have a snake child. So that's the pattern we're matching. Okay, what are we going to do in this case? In this case, it's time to get rid of the apple core completely. And in order to grow the snake, we're going to add a new snake child at the same location. And we're going to tell it to follow its leader, which means to move in the direction of the child that used to be the last child. So now we've grown the snake by 1. And we also want this rule to apply in all 4 directions. So now, as you see, if we go over the snake, as soon as the last child goes over the apple core or passes it, then the snake grows. And so at some point we can run into ourselves. Oops. All right, so that is the demo, complete demo of the snake game, which took us 9 rules in all. So I hope you've appreciated the TileCode program you've seen. TileCode was designed to be a visual language to have a sort of close mapping between English and rules. So we have a way to read out in English the meaning of a when-do clause. We don't have to think about the entire program at once. You see that parallelism and pattern matching are the primary structuring mechanisms. Pattern matching takes place in the 3x3 grid around a central sprite, and the patterns apply wherever they match on the TileCode tile map. This is quite different than what you have probably experienced or might have seen in game programming environments that use blocks, such as Scratch or Make Code. The emphasis there is on composable coding blocks using the Blockly framework, where you can drag and drop blocks together to create essentially a structured program. Structured control flow is really the primary structuring mechanism of these environments. And although they have the ability for concurrency, the emphasis is really on sequential programming as opposed to data parallel pattern matching, which you've seen in TileCode. TileCode was created really to be able to run on these very small devices and to have an editing paradigm that would fit with the tile map games, whereas Scratch and Make Code have the ability to express a wide variety of games, not just tile-based games. Most importantly, TileCode works on small devices like this Meowbit. So here you can see the home screen of TileCode, and if I press the D-pad button, you can see the cursor moving around.
Now I'm going to tell you a little bit more about our user study and the workshops we've done together with families over the summer. In our study, we had 16 families from all over North America that participated in 4 to 5 weekly sessions of 45 minutes. Each family was given the opportunity to engage with coding activities at home and also participated in these sessions with the researchers with us. We took field notes from each of the sessions and also recorded the sessions. I'm going to show you a video where you can get an overview of how the children and the parents engage with TileCode over this study. Now, in our study, we had this 4 sessions, so I will present what happened in each session of the study. In the first session, the family watched, described, and modified 3 games. We presented them with the game of Snake, which Tom presented earlier, Boulder Dash, and Bejeweled. In a second session, we asked the families to complete a form for designing their own game using TileCode, and then start to build it. In the third session, we presented the families with a rich vocabulary of game patterns and coding patterns and encouraged them to pick only 3 of these patterns and combine them in a game that they would like to build. Lastly, in our final session, we allowed the families to, again, watch 3 videos of 3 video games built with TileCode and describe how these games work. The final video games were Pac-Man, Space Invaders, and a conveyor belt game. What we found in our study was that overall, the children and the parents were curious about how the video games work. And initially, they engaged in various levels of richness in the way they were describing these games. All the families had ideas about how to make the video games more fun. But initially, they had a limited ability in scoping how they would like to make these game changes. In the second and third session, what we saw is that children started with complex game ideas. Many of our participants actually wanted to build Minecraft in TileCode. We saw that older children inquired about the platform abilities and tried to scope their designs according to what the platform can do. Most of the time, children will spend a long time in designing the characters of the game and the backgrounds of the game, in creating the assets of the game. And as they were going along and learning how to build the different rules and code their games, sometimes they would update their game narrative just so it would be able to fit the rules they knew how to program. Once they had a story in mind, the narrative piece was quite important. Children weren't so intimidated to start coding. It's almost like they were very motivated to make their character come to life, to make their game come to life. Another thing we found at the very end was that most of the participants guessed the correct rules in our final Guess the Rule game. And that their descriptions, their final descriptions of games, got much more complex. They were able to create direct parallels between game events and the rules that were associated with creating these events. We had much richer descriptions in describing these games, both from the kids and parents. And overall, we found that children and parents collaborated and engage in a balanced way with the platform and with the game creation throughout the study. I'm going to show you some examples of children games that were built in this study. The first example is a race game. So this was a very simple game that was built by a 10-year-old girl in the very first session of our study, where she had 2 animals, a dog and a squirrel, as she described it, trying to race towards the finish line. And the game was very simple because she learned how to make the dog move by itself, and then the goal of the game was to actually try to move the squirrel faster than the dog in reaching the finish line. And this was fun because the automated movement for the dog was quite faster than the player could move the squirrel. So by default, the player would lose the game all the time. So then programmatically, our young participant had to figure out how can she slow down the automatic motion for the dog in order for the player to have a chance to win. So this was an example of a very simple game built only with 3 rules, but which was very engaging both for the family and for other players. Another example was this double snake game. Just like in the demo that Tom showed earlier of the snake game, we had this demo for kids. However, we had a family where the first modification that our siblings in this case tried to make was to create a double snake. So besides the original green snake, they made a yellow snake, which was trying to compete with the snake controlled by the user and eat the apples first. So it was like an automated snake moving across the screen, which was not controlled by the player. The third game was the underwater game. So in this game, we had 2 siblings that created a game about an explorer that would go underwater and try to move across different type of coral while collecting the diamonds and trying to stay away from the shark. The way the explorer would win this game is by reaching the end of a maze made of coral. So this was quite a more complicated game with very intricate map, and the siblings in this case created all the backgrounds and the game levels. So this was a type of game that they made at the end of the study. So what we can see in these 3 examples is different levels of complexity of game mechanics and of programming rules. However, we see that children were able to identify at different stages of the study how to use the platform and were able to create their own games and their own rules with the platform, disregarding of how much experience they had with TileCode. Another thing we found in this study was that the parents played a crucial role. Many times when the children would not understand one of the concepts or the terms used in our platform, the parents would step in and were able to explain in a language that their children understood what the platform does or what's expected from them in a specific instruction of the game. And moreover, the parents knew what their kids are into, so they would always prompt them like, you like going and playing with this type of game, why don't you try to do something similar to that? We also saw that the children would spend more time and would be more engaged with the platform if their parents were around and they were involved. So in general, one of the important lessons, especially right now when children are mostly learning from home together with their families, for us was to think of how we design not only for children but also for parents and for family learning. We've seen a lot of opportunities for creative personal expression in our study, especially when watching how much time children would spend in creating their own characters, their own backgrounds, and we see a lot of opportunities for sharing these assets in future versions of TileCode. Believing that it's quite important, like one simple element in the background or one change like in the character will lead to a completely new story, a completely new opportunity for creating a new game. So allowing users to be able to share these assets and these ideas would lead to much richer engagement with the platform. In the study, we also have seen a lot of parallels between gameplay design and game programming. Just like in a gameplay design, user has to create a game plan and it has to be aware of the game state. We have the game goals and the game rule mechanics. In the case of TileCode and in the case of game programming, we need to make a game program design where we also keep track of the machine state, in our case the map, and where the objects are on the map. There are goals for the game, and there are rules and mechanics for our system, for our machine, and for our program. So we see TileCode as a unique opportunity for teaching children about powerful computational ideas because it builds on this low entry point of video games that are very appealing for kids, but it has a direct analogy and a direct parallel with concepts from computer science that are more easily presented to children in this scenario of a game planning rather than a program planning. To conclude, we saw in this user study that TileCode can be a playground for powerful ideas, and it became this playground for powerful ideas because it allowed both children and parents to code, play, and update their game data as they went along. So allowing them to engage with video games from these three different perspectives at all times was extremely useful, and it lowered the barrier of entry for people that didn't have a lot of experience with video games and with programming before.
I hope you can appreciate that through the programming demos as well as Steph's user studies, that there are some really powerful computational ideas in TileCode. We've seen notions of data and state, local knowledge, pattern matching, parallelism, conflicts. What I didn't show you was randomization. There's an underlying logic. So there's a lot of really great ideas to discover there in a very, very small language. The next steps for TileCode, we have thoughts based on the user studies we did on improving the language and the user interface based on our learnings. We're also thinking of a web app that takes us into the realm of touch and gives us more possibilities for interaction, as well as potentially the incorporation of natural language as informal specification. Finally, we think that it would be interesting to look at how to make something like TileCode more accessible, especially with incorporation of natural language. If you want to learn more about TileCode and experience the web app yourself, then please visit aka.ms/TileCode. You can get access to the web application there. TileCode is open source on GitHub at this URL, and TileCode is built with MakeCode Arcade. And so I also encourage people to check that out as well. Steph and I wrote an introductory blog, which you can find here. And with that, we would love to have your questions in the question and answer period to follow. Thank you very much.
Hello, everybody. This is Tom Ball with Stefania Druga.
Hello.
Hi, Steph. Thanks for attending this webinar from Player to Creator, Designing Video Games on Gaming Handhelds with Microsoft TileCode. This is a live Q&A, and over the next 15 minutes, we're going to be answering top questions submitted by you, the audience. Let's get started. Steph, do you want to take the first question?
We have some pending questions from the chat as well, if that we can go to before we get new questions. So I know there were a couple of questions around from Vidimnas around learning outcomes and how TileCode compares with other existing programming languages for kids. And then, you know, like how will it support, if it doesn't support yet, the online learning and remixing or collaboration? In terms of learning outcomes and how do we measure what children learn, in our initial user study, and this is the first user study that was done with TileCode, we took an approach of not focused on instructionism, but more focused on constructionism. So we actually wanted to see if children that never programmed with TileCode before or that had limited prior coding experience were actually able to create their own games. And we wanted to look at how different these games would be, how well were they able to translate their ideas, their initial concepts for a game into a game they were able to program and play with their parents or their friends. So that was something that was our approach for measuring the learning in our user studies, but we also looked at language. So we actually wanted to see how children and parents develop a personal ontology around the way they describe video games and the way they describe programming concepts used in these video games. So it turns out that in the very beginning, many of the families, when they were asked to describe video games, like that they would see in videos, would have more simple descriptions or would not be able to identify as many elements of the game or events or elements in the background that matter. But when they got the chance to get their own experience with programming these games, not only did they develop a more rich vocabulary, but they were also able to just perceive and observe many more elements in the game that matter. So I think that was this was our approach to observing, analyzing, and designing for supporting learning during these workshops and activities with families. But it's only the beginning, so there's much more to be done there.
Great, thank you, Steph. We have another question about the limitations of TileCode. You only allow 4 sprites and 4 backgrounds. It's restrictive, and yes, by design, TileCode is meant to be quite a restrictive little sandbox. But I think what we've seen is that you can actually do quite a bit of expression within that. Certainly, the design of TileCode was made so that it can really run on low-cost handhelds. In fact, the Meowbit that I showed in the video only has 96 kilobytes of memory, yet you can put 8 different games in it, and so it's restricted by design. But in the future, we definitely imagine having more powerful handhelds that could have more sprites, as well as maybe a richer sort of programming interface. So thanks to Pedro for that question. Steph, would you like to take one?
Yes, so I see Sydney asked us, I'm guessing Sydney is a parent, and she asked us lots of games now, especially mobile games, that many children have exposure to, are more immediately rewarding. Did the children show a preference for more complex games that they didn't have to make themselves? This is a really good question. I think definitely, the emergence of tools like TileCode and any other new programming platform for kids tackling video games doesn't happen in a void. We need to be aware and take into account the media ecosystem in which children and families are finding themselves these days, especially with the learning from home, especially with the increased time on online. So one thing I can tell you is that I was actually surprised to see how many of the children actually wanted to start with very complex games. So we had 3 families where the first game children wanted to build on TileCode was Minecraft. And as you can imagine, that is quite challenging. We definitely came up with creative ways of representing a 3D world into a 2D world. Like how could we make the sprite move slower to simulate this climbing, a hill, for example, or things like that. These were some of the ideas we had. But in general, I think once children understood how the platform works, they didn't shy away from complexity. On the contrary, and I think like one of the things that is quite powerful about TileCode is that it provides this different perspectives. Like if the children get stuck with the rules, they get stuck in the code, they can go to the map and change the map. They can go to the sprites and add a new sprite, or like maybe transform even these limitations that Tom just talked about. Like we only have 4 sprites, but we have 4 backgrounds. Maybe we need an extra sprite. We will use one of the backgrounds be a sprite. So like a lot of the constraints actually fuel their creativity, and they had to work around these constraints. And I almost think that was helpful. And I didn't see them shy away from complexity. I think the main difference between the immediately more like Candy Crush or like the immediately rewarding games that children have access to and the games they build themselves is this notion of agency, that they are in control of what happens in the game. They can create their own character, they can create their own game art, they can make their own rules, they can make a game that is so impossible to play that they are the only ones who know how to win, and they like that. And actually, that's what we were trying to do, is to allow children not to be only consumers of commercial games, but maybe start on some of these elements of video games that they like, but allow them to be creators as well.
Great. Thanks, Steph. There are two questions, one from Ross and one from Vidminas about sharing and remixing. And that's definitely something that that is for future work in TileCode. Right now, when you put when you're in the web browser, the game state is saved locally in browser local storage, and when you're on a TileCode device such as the Meowbit, the program the game assets, rather, the programs, the sprites, are stored in flash storage. And we don't have a good sharing solution implemented. What is possible, though, is that when you've created a game on a handheld device and you plug it into a laptop or a desktop, it appears as a mass storage device over USB. And you can drag, essentially, the TileCode program out of, you can copy it off the device onto your desktop or laptop. And when you do that, all the settings that contain your game assets are stored in that file. So then if you take that file, you have the game assets, and if you were to give it or email it to a friend who had a Meowbit, they could install that same file, and then they would see your games. So it's a very low-level type of sharing. We really want to have a much free-form solution where, regardless of where you create the games and the game assets, you can share them. So clearly, the web app needs to be able to export game assets to the gaming handheld and vice versa. And we would obviously also like to encourage sharing, when you have an internet connection over the web. Another idea that we have is we do have the ability to network the gaming devices. So for example, if you had a game on your arcade handheld and a friend had one, another handheld, you could connect them via a cable and just battery powered, and potentially have a user interface to share the game, to copy it over, or do multiplayer. So there's lots of interesting aspects to sharing as well as remixing, and we intend to explore that in the future, but we're going to need to create some more infrastructure for that. Great questions. Thank you very much. Steph, I'll hand it back to you.
Yeah, we have a question from Gayatri. She asked many great questions. And this question is asking about the role of parents. She's asking if we see any interesting ways in which parents describe computational ideas while teaching their kids, any analogies, metaphors, anything else. And the short answer is yes, many ways. They were much better at describing and translating some of the computational ideas to their kids than we were, because they know their children better. There was a reason why we did this study with families and not only children. And I think in today's world, and especially with all the online learning, parents find themselves much more involved in children learning, not only of computational ideas, but in general. And in my research, I've been working with children and families for more than 8 years now. I always found that having parents involved plays a huge role, especially from a social emotional perspective. Children love to have the validation of their parents when they build something, be able to share that, be able to have their parents' encouragement. And the type of workshops or the type of engagement one would do in a classroom or in an informal learning setting only matters if it's further encouraged and supported at home. So in my work and in my research, it's very important to work with parents as well, and not only with children, work with families. Specifically in our study, it was interesting because the TileCode interface and programming paradigm is new for kids. So having parents be there and help us build some conceptual bridges was essential. And very often they would know how to reference this to an experience or another game that the child played or something the child liked that we didn't know. I had the case of a mom who where her daughters were asking why the princess looks very different on the map versus how it looks like when we're building the rules. And she had to explain, downscaling resolution to her daughters in a language that I would have never known how to use or how to formulate. And it was just incredible to see that actually even very young children, as young as 7, could understand this kind of concepts if explained right and with lots of examples. So I think this was my favorite part from our user study, the fact that we could work with families, that when the parents had the time to get involved, it showed it really helped with children getting to do more complicated projects faster. So I actually think it's important for many other tool designers and technology designers to design for families and not only for children.
Great, thank you, Steph. Steph, you have another question. Maybe you can hop to right now from Didminas, who has a question number 30.
Yes, Vidminas is asking if after the user study with 7 to 12 years old, we think the platform worked well with this age group, and if we would test the age range when testing again. We think that the platform worked well for this age group. Obviously, the older children were able to build more complex projects faster, but the 7-year-olds, 8-year-olds were able to engage with the platform, and they enjoyed playing with the platform. They enjoyed building their own games as well. So it wasn't the younger children and the older children both enjoyed and were able to engage with the platform. It was more of a difference in level of complexity of the games they would make. And one thing that Tom and I talked about, and there are many future steps for TileCode, which I'll let Tom talk about more in a second. But one potential way to mitigate the age difference is to provide more beginner version, like with some of the features be enabled or automated or hidden, and then have this kind of progressive disclosure as the users become more familiar with the platform. I know someone else was asking about this, if some of the features are by default enabled to a specific mode. That's something we played with during the study as well. For example, do we make certain rules generalized? Like when we have the main character of the game that the camera follows, and we made a rule to teach the character to move to the right, do we want that rule to apply to left, to up and down, or do we need to make 4 rules, which can be very tedious, right? So we actually made the decision to generalize certain rules, but sometimes, children had different intuition about how the rules should generalize. So this is, there are a lot of research questions here which are still worth exploring and testing, and maybe have more user studies, definitely have more user studies, larger group of participants. But in terms of age, I think this worked well, even if the age range in our study was quite broad. And I think for future studies, being able to have some sort of progressive disclosure feature would be very helpful.
Great. Yeah, thanks, Steph. Yeah, there's definitely a lot of complexity you can get into with TileCode, and thinking about scaffolding or starting with very simple rules and then increasing complexity, and doing that with some support in the UI is definitely something we want to look at. Daniel also asked, and maybe this is a question both of us have to try to answer. He said, in the example of the game with the shark, how do you link the shark with the main character? How does the shark know the current position? So by default in TileCode, the first sprite, the sprite on the left, is the sprite that generally the camera follows. We haven't done a good job yet on sort of separating the sprites. Any sprite can be user controlled, but the camera follows the first one. Again, the sprites can only respond to one another essentially by this pattern matching in the 3x3 neighborhood. So there's, if sprites are separated by a long distance in the matrix or the grid, there's no way for them to know the coordinates or the existence of the other sprites. That's by design with this sort of cellular automata approach. Everything is done locally. So I hope that answers the question, Daniel.
And I can give an example as well of how this played out.
Thank you, Steph.
Yeah, so sometimes, you know, like because in other platforms like Scratch or Alice, or like the coordinates of the characters matter, and like we build programming logic based on the XY position. Here it was different, like because the camera was just following the explorer, the sharks were in the maze, and the sharks, like the children learn, for example, how to animate the sharks, like just like in the game with Snake in the tutorial, like some children wanted to build a second snake that would just like go around the screen by itself. So other characters can be animated and they will appear in the camera even if the camera is not following them, and then build a collision rule. So what happens if the explorer runs into the shark? Then, you know, the explorer dies. So there's a collision rule for what happens when these two characters meet. And then, of course, like for animating the shark, like for deciding when and where does the shark move, there were lots of ways to do that. So either by deciding the shark should always move when it's in a certain type of background, or it should move if it hits something, or so children got to play. It was more this kind of designing for emergent behavior and creating rules for what happens if certain characters meet, or certain characters meet with a specific background and things like that. But it was a different logic than trying to account and keep track of specific positions for each character.
Yeah, thank you, Steph. Yeah, there are no arrays. There's no iteration over arrays. It's all sort of implicit by the pattern matching, and that's something that I think is quite powerful. But it also can yield some surprising results because you're doing all this pattern matching in parallel.
I had a question I wanted to go back to from Charlotte about.
Yes, please, of course.
Charlotte is asking us if there's any plan to offer AI control non-player sprites in the future. And I love this question because actually kids asked us this too. And I remember at some point, like when their games were getting more complex, and we had an 8-year-old boy who's like, why can't I just make TileCode generate the levels? I'll tell it like I need 7 snakes, and so they were like looking for automation of certain parts of the platform. Kids also asked us for voice support for debugging. They were like basically asking us to replace ourselves as facilitators, like when the study is over, which was interesting. My research focuses on AI education for kids, and I'm right now actually looking specifically at program synthesis. So trying to see if there are any ways for the platform, even if it's in TileCode or Cognimates, which is a platform that I built, or other programming languages where the platform itself can support the users either to build the right rule or to build rules that would be complementary to what they're doing, or to generate like random elements on the map. So this is really, I think, the future of coding for kids, and there's so much to explore there. And one thing that I would encourage the folks who are still with us today to think about is to really think about new opportunities for learning that this could open up, and not only from the perspective of we have this programming concepts, we have this like computer science theory, and we need to see if kids will learn it well. More like, what are all the ways in which they could create with these tools? And are there new ways for them to create and code with these tools that were not available or possible before? How can we create new mediums for them? So I think there are a lot of exciting future options, and I know Tom also looked into program synthesis for TileCode, and I'll let him talk more about that.
Yeah, thanks, Steph. Yeah, the sort of the data pattern matching of the cellular automata turns out to be very closely related to convolutional neural networks, and you can actually take sort of TileCode programs and run them and have a neural net sort of learn rules. We haven't done that, but there is research. So I think having this sort of notion that of computation as a big part of computation is this pattern matching. As the patterns extend from a 3x3 grid, to a chessboard size, to larger size, you're going to need to recognize patterns, and you might not be able to code them all by hand. So how are you going to do better pattern recognition? So there's really a fascinating question there as well, and I think I think that's very interesting. So I think we're at 1 hour. So I think we have maybe one more question. That is question 31. Steph, I think this one is for you. So why don't we make that our last question? And if you have more, you can please ask them. We'll try to answer them offline.
Vidminas is asking about future resources to learn about theories, academic background that are relevant for the user studies we talked about, and the research project idea. I was going to put my Scholar link and send it. There are a lot of different theories. Like, we looked at the theory of cognitive continuum, and basically how do we build on initial children's intuitions around the concepts that are being presented in the video games and on the platform. And then over time, either through facilitating not only the engagement with the platform and the prompts they get on the platform, but also facilitating the engagement with their peers or with their parents, they can move from an intuitive way of thinking to a more quasi-experimental way of thinking. So there are a lot of theories around collaborative sense-making, for example, that apply here, and the work of Andy DiCessa in Changing Minds and building on P primes for kids is very relevant as well. So basically what we want is to enable the children to become tiny scientists, like for them to build a lot of different hypotheses and have the tools and platforms that support them to test these hypotheses in a more seamless way. Because in that way, they will be able to prototype and test many more ideas. And if they have wrong assumptions, correct them on their own terms.
Great. Thank you, Steph. We'd like to thank everybody for attending today. We really appreciate your participation and interest. If you want to learn more, we have a bunch of resources in the resource list to the right of your screen. That includes the website, which has the Microsoft TileCode web app, as well as documentation and videos pointing out how you can create your own games. We also have a project homepage and a paper if you want to read more about it. We really look forward to seeing how you build on this research. We welcome suggestions too. Please email us at tilecode@microsoft.com. And that's all. Thanks very much, and have a great day, everyone.
Thank you. Take care. Thanks for joining.
Thank you, Steph. Bye-bye, everyone.